Okay, we are back. It is Calculus 1. This is 4.5, Part 2. We're going to do 17 through 21. So, page 17 on the note packet for Chapter 4, we're talking about concavity. Like concave up means it kind of opens up like a cup, like it would hold water. Concave down means it's going down. So sort of like concave down, concave up. So let's see, opens up, F prime is increasing, F double prime is greater than 0. So when it's concave up, when it opens up, concave up, the second derivative, the first derivative is increasing, the second derivative is positive. That means concave up. So it's going to look like this. Concave up. If the second derivative is negative, less than 0, then F prime is decreasing. And that means concave down. So let's look at the examples they have. I drew the pictures up on the board already. So when it's a parabola, it's all concave up. It never is opening down. It's up, 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 up. So negative infinity to infinity. Now, on the test, you have to write like none or nowhere. Don't just leave it blank if it's not concave down at all. Say none or nowhere. If I just see blanks, then I mark it wrong and figure you didn't know what you were doing. So when there's a blank, put something in the blank. Don't just leave it blank. All right. So concave up. Where is it? This one concave up. So this is sort of like the cube, y equals x cubed. It's like this is half of a parabola and this is half of a parabola. So if I took this and drew the parabola and then reflected it over, that would be that part. And so the concavity, it might not be super easy to see, but this is where it stops going, like where it stops going concave down and starts going concave up. That's called a point of inflection, an inflection point, an IP, and we're going to get to those too. Next page. All right, so where is this one concave up? From 0 to positive infinity. This part is concave up. And where is it concave down? That's negative infinity to 0. That's this part is concave down. All right, this one's a little more interesting, cubic, but it's got minus 3x and plus 3. So we go a little up, we go a little down. It's not just a boring cubic like that. So where is this one concave up? Well, concave up means like this. So that's from 0 to infinity. And concave down then is negative infinity to 0. That would be like this part. All right. Now, the cosine curve, y equals 3. This is y equals 3 times the cosine of x. So that's interesting. It goes up to 3 and down to negative 3. That's no big deal. But there's continuous concavity changes. This is concave up, that part. This is concave down. This is concave up. This is concave down. This is concave up, right? Concave down. And so it continuously flips from concave up to concave down, or vice versa, depending on where you started. So we will say from pi over 2 to 3 pi over 2. That interval is concave up. That's from here to here, from 90 degrees to 270 degrees. That's concave up. But then plus pi n. Every 180 degrees, you get another, concave up, another concave up, another, another 180 degrees. So n could be positive or negative integer. We'd have to say where n is a positive or negative integer. So I could say 4 and then plus 4 pi, and that would be concave up on that interval. And so on and so forth. At -2, it would take it this way, but it would be a continuous where n is any integer. It can't be a decimal number because then it would throw off the 180 degrees. All right, and then where is it concave down? From -90 to 90, -2, pi over 2 to pi over 2. So from this interval, and then again, every 180 degrees, it happens again and again and again. So plus pi n. So that's an interesting little look at concavity. All right. So again, concavity is the curvature of the graph, how it's curved. Is it opening up or kind of opening down? All right, let's look at page 18. So page 18, they have use the theorem. Okay, what is the theorem? Let's fill in for the theorem, a little box on the top of page 18, F double prime. So 2 little hack marks of x is greater than 0 for every value of x in I, in the interval, then f is concave up. So when the second derivative is a positive number, that interval is concave up. When the second derivative is a negative number, less than 0, that means concave down. And again, we'll kind of do concave up, concave down. You can draw little pictures like that. Okay, let's take a look. Use the theorem to test A, B, and C. Oh no, just A and C. I don't know. We didn't do a B. Weird. Okay, verify your answer with the graph. Okay. So here we go. Y is equal to x squared. The first derivative of that is 2x. The second derivative is 2. Well, 2 is a positive number, so 2 is greater than 0. So if the second derivative is greater than 0, we're talking about concave up. Pretty much on the entire interval of the graph. There aren't any inflection points. And then if we look at that graph, that is the parabola. We actually did that on the first page from -infinity to infinity. It's all concave up, all opening up. All right, let's look at C. I think that's a typo. I think that was supposed to be B. X cubed minus 3x plus 3. So now we do the first derivative. That's 3x squared minus 3. The second derivative, that's 6x. And now we'd have to look at intervals here. So we'd want to know where would there be a possible point of inflection. So we'd say 6x, you take the second derivative and set that equal to 0. Okay, so 0. So x equals 0 is a possible point of inflection or inflection point, an IP, possible IP. So this is how we do this. Hold on, let's do a little separate. And so we're not going to look at the graph right now. We're going to do it like this. We're going to put a number line. And we'll mark it with an arrow, our critical number. This is a critical number. 0. All right. And now we're going to look at either side. So this is the interval from negative infinity to 0. This is the interval from 0 to positive infinity. And the concavities could change from here to here. So what we do is we pick any number that's negative infinity to 0. So you could do negative 100 or negative 50 or negative 1 and positive 1. And you just pick numbers. You could pick 2 or 3 or 5 or whatever. And then you take those and you put them into the second derivative. So we're going to do the second derivative is 6x, but we're going to do 6 times negative 1. That is negative 6. Negative 6 is less than 0. So that means the second derivative is less than 0 on this interval. If it's less than 0, that is negative, and that means it's concave down. So we have concave down there. All right. We then take any number from this interval, from 0 to positive infinity. And so that I just went with 1. That is positive 6. Positive 6 is greater than 0. So the second derivative on that interval is greater than 0, which means that's positive, which means that is concave up. And so if we switch from concave down to concave up, that means we have an inflection point. This is a point of inflection, or IP. IP at, I'm not sure why I do the little at thing. I'm horrible at the little at symbol. I could just write the word at. That's probably easier. IP at x equals 0. So there's an inflection point at x equals 0. And so that's what we were after there. All right, let's look for, now they discuss inflection points. If f is continuous at A and f changes concavity at A, at point A, the point A comma f of A, that's x and y, is an inflection point of f. All right, and so that's sort of what we just determined here. All right, so let's erase this and we'll look at the pretty picture on the bottom of page 18. So we've got, I don't know, if the graph didn't come off great on yours, this is what it should sort of look like this. All right, and the inflection point is right there. And so this part of it is concave down. This part of it is concave up. And this is the original graph. This is f. That's not f prime or f double prime. That's just f. So we're just looking at concavity, points of inflection. So if A comma f A is an inflection point, then f double prime of A is going to equal 0. And or f double prime of A is does not exist. That could also happen. But the original function f must exist at A, so it cannot be an asymptote. It's got to exist. Must exist at A. All right. Let's to page 19. Okay, so plan on writing small. If you are filling in the packet, this is what you have to look forward to on this one. It is one heck of a problem set here. I'm going to be erasing the board several times. Okay, so page 19 is a doozy. If you took a look at that and went, oh, you know what, I'm going to switch to lined paper for this page, that's fine. When you send it to me, just throw the lined paper in there with it, and that's fine. If you're going to skip it and put the lined paper at the end, maybe put a note on the packet, because I kind of check it a page at a time, and I don't always look for other attachments. Or the fact that you had like 40 pages in a 30-page packet or something, and so say, you know, see lined paper at the end or something. Because otherwise I'm correcting it, and then I did that already, or I corrected somebody's stuff and then went and found all of it and then changed. I did change the score. I didn't say, I'm just keeping it. Okay, so we have to do, so here, wait, let me start. Too busy yapping about correcting. So let's take a look at example 3. This is f of x equals 2x plus 1 quantity cubed. So we have to do the first and second derivative of that, and then set it equal to 0, and then find inflection points, and then see where they exist. So find the intervals of concave up and concave down, and any inflection points. All right. And okay, that's for number 4. All right, so this one is pretty straightforward, but we have to remember our derivative rules. So 2x plus 1, and then take 1 off, squared. But then you have to multiply it by the derivative of what's inside. So there's a 2 there. So f prime of x is actually 6 times quantity 2x plus 1 squared. Now, f double prime, you take the 2 times 6, you get a 12. Again, we leave the 2x plus 1 intact to the first power. You don't have to really say that. And then times 2. So f double prime is equal to 24 times 2x plus 1. And you leave it like that. Don't multiply the 24 in. I know sometimes we kind of simplify right away, but remember, we're going to set this equal to 0 now. So if you just put that in there, the next step is going to be to factor the 24 back out. And so let's leave it like that. 24 times 2x plus 1 equals 0. Divide out the 24. 2x plus 1 equals 0. Get rid of the 1. Divide by the 2. So x is equal to negative 1/2. So now the question is, that's our critical number. We're going to look and see about the inflection point here. So what we want to do is set that up. So let's set it up in just a number line interval. I always put an arrow on your critical number, your inflection point. Negative 1/2. All right? And so negative 1/2, we want something to the left, something to the right. When we set up the interval, negative infinity to negative 1/2 and positive, or negative 1/2 to positive infinity. Those are the two intervals that we're checking. So this to the left of negative 1/2, I'm going to just say negative 1. You could say negative 2. You could say negative 5. You could say negative 10. You could do any of them, any number, just so it's to the left of negative 1/2 on the number line. To the right of it, I'm definitely using 0. 0 is an easy one. So anytime you can use a 0, toss that in there. So, okay, we're looking at the second derivative. So f double prime of our critical number, which in this case is f double prime of, or not of our critical number, we're just checking the interval. Sorry. Scratch that off. f double prime of our test number here, -1. And we want to see, is that positive or is that negative? And so I toss in -1 here. And again, putting it in here instead of having it all distributed makes it easier, because you can do -2 plus 1 is -1. So 24 is -1 is -24. And so if you know it's -24, we know -24 is less than 0. So f double prime of -1 is less than 0, which means it's negative, which means this is negative, and so it is concave down. Won't hold any water, concave down. All right. So the entire interval from -infinity to -1/2 is concave down based on that test point. Let's go double prime of 0. So that, again, you go back here, 0 times 2 is 0, plus 1 is 1. And so 1 times 24 is just 24. And that is positive. So f double prime of 0 is greater than 0 or positive. So that's concave up from -1/2 to positive infinity. That whole is concave up. So if we're changing from concave down to concave up, we have ourselves an inflection point. At x equals -1/2. Don't just say at -1/2. If you leave off the x, I know it sounds very nitpicky and you're like, oh my gosh, the guy just loves taking off points. It's very important that you're precise. If you say, you know, the IP at, and just say -1/2, that's not specific enough. You have to say x equals -1/2. We are always giving intervals in terms of x. This is in terms of x. That's in terms of x. All right. And so make sure you put the x down. Okay, there's number 3. Let's look at number 4. So f of x is equal to x squared plus 3 over x squared minus 4. And we could look at the domain. So if we're going to do the domain, if it was just x squared plus 3, it would be all real numbers, no problem. But because there's a denominator with a variable in it, we're worried about zeros in the bottom, crashes it, right? So if we say x squared minus 4 is equal to 0, and then we factor x plus 2x minus 2 equals 0, that means x equals -2 will create a 0, and x equals +2 will create a 0. So if I put in 2 or -2 into this, it'll make it 0 on the bottom, which creates a vertical asymptote, which gives us domain restrictions. And so it can't be that number. It can't be that number. But when we identify domains, we use interval notation in calculus. So we'd say -infinity to -2, and then put parentheses on it. That means it doesn't include it. In union with -2 to 2, parentheses, means it doesn't include the -2. And then in union with 2 to positive infinity. So that is the domain. So if a 2 or a -2 comes up, then we're gonna, those are asymptotes, and those aren't gonna be inflection points. But we can still determine the concavity on either side of the asymptotes. So by doing the same process that we did before. All right, so we got to take a couple of derivatives. So that was just a little sidebar on the domain. So how do we, I hope you remember how to do your derivatives. It's low D high minus high D low over low. So what did we do there? We wrote that down. We did the derivative of that was 2x minus, we wrote that down. We did the derivative of that is 2x. And then we squared the bottom. And so when we clean that up, let's clean that up. We end up with here, to try to save space here, let's just do 2x to the third minus 8x minus 2x to the third minus 6x. Right? Because you got the negative 2x times x squared plus 3. So you get negative 2x cubed minus 6. And so then you combine up those like terms. And we get negative 14, right? The 2x cubes die, negative 8 and negative 6, negative 14. X over x squared minus 4 squared. So there's our first derivative. Lovely. Let's find the second derivative. And again, we're going to do the quotient rule. So what is that? Low D high. Low derivative high minus high D low. Ooh, the derivative of the lower is got a bit of a problem, right? We got 2x squared minus 4, and then to the first, and then times the derivative of the stuff inside. So we have the quotient rule and the chain rule. All over low. All right, and yeah, let's clean that up a bit. What can we do? X squared minus 4. So here, let me rearrange it, and we're going to do a little spring cleaning here. We've got negative 14 times x squared minus 4 squared. Two negatives in a row make a plus, and we got 2 times 2 is 4 times 14. 4 times 14 is what, 56? So 56. X squared times x squared minus 4. All right. So now what do we have? Well, we can factor out on the top an x squared minus 4. Because look, this is just two terms, this one and this one. So I can pull one of them out. This only has one. So that's why I can't do 2. So I'm going to factor that out and cancel off one of them off of the bottom. So follow this. We are factoring out an x squared minus 4. And then we're left with negative 14 times an x squared minus 4 plus a 56x squared over x squared minus 4 times x squared minus 4 cubed. So I just separated one of those out so I can cancel it with this one. And now let's distribute that and then combine like terms. So we got negative 14x squared plus 56x squared. So this was one bear of a derivative here. 42x squared plus 56 over x squared minus 4 cubed. All right. Whew. So lots of derivative work there, especially with that second derivative. That was a little complicated. Okay, so, and everybody sees this, right? It was negative 14x squared plus 56x squared. That's how we got 42x squared. And then negative 14 times negative 4 is 56. And then now we're that cubed. All right, so we're going to set this equal to 0 and this equal to 0 and look for critical numbers. So we're going to end up with just, I think, 2 critical numbers, because when we do 42x squared plus 56 and we set that equal to 0, we end up with x squared equals negative 56 40-seconds. And I know we could reduce it, but when you take the square root of a negative, you're putting it into the complex number system. And we're keeping it real. It's real numbers only. So that's garbage. It's complex. Complex solutions. The imaginary numbers. And so we're not working with imaginary numbers. We're sticking in the real number system. And so the top doesn't have a 0, basically. If you think about it, if you logic it, look, any number you put in here, you're going to square it, which is make it positive, and then you're adding 56 to it. So there's no way to get a 0 up there. Because even if I put in -1, -1 squared is 1, and then times 42 plus 56, it's always going to be a positive number. So no complex solutions, so there's nothing off of the top. Off of the bottom, we already have looked at this. X squared minus 4 cubed is equal to 0, so we could take the cube root of both sides to get rid of that cubed, but that's just 0 again. And now we got the x squared minus 4. We did that right there. So we know x equals 2 and x equals -2 are those asymptotes that we determined when we looked at the domain before we even started the problem. So these count as critical. So that's going to split up our concavities into 3 pieces. So we've got 3 intervals. We've got these 3 intervals, actually. Negative infinity to -2, and -2 to 2, and 2 to positive infinity. Those are our 3. So 0 is a good number there. 3 or 4 or 20 or 100 or whatever you want. Just keep it simple, I think. It's 3 and -3. And so now we want to do f double prime of -3 to determine the concavity. There won't be any inflection points, but we can look for concavity changes. All right, so let's see. I put in a -3 into, where's our double prime here? There. Oof. So -3 squared is 9 times 42 plus 56. And 9 minus 4 is 5 cubed. So 125 on the bottom. And so when you divide that out, I think you get approximately 3.472, which is positive. So f double prime of -3 is positive. So that means this is positive. So that is concave up. F double prime of 0, we like 0, is easy, right? So 0 goes there, 0 goes there. We got 56 over -64. That's about -0.875. And that is less than 0. So f double prime of 0 is less than 0. So that is negative. And so that is concave down. That's not going to hold any water. And f double prime of +3, that's going to equal, the same thing, I think, as this did, 3.472 again. It's more than that. That's an approximation. That's greater than 0. And so that means the second derivative at 3 was positive, and positive means concave up. All right. So yeah, I think that's where the show ends. There are no points of inflection. We just have these things approaching these asymptotes forever, but the concavity is consistent in each one of those. So, you know, we could say concave up for negative infinity to negative 2, and for, or yeah, I think we could use the union sign there. 2 to positive infinity, and then concave down is just from negative 2 to 2. All right. Whew, that was a mouthful for number 4. Let's look at number 5. That's got a little trigonometry in it. All right, so we got y is equal to 2x minus 2 tan x from negative 90 to 90, or negative pi over 2 to pi over 2. Not brackets, parentheses. All right, so our domain is, we're worried about where the cosine, because tangent, remember tangent of x is equal to sine over cosine. So if we're worried about our domain, that would be where the cosine of x equals 0. And again, remembering 1, 0, 0, 1, negative 1, 0, 0, negative 1, coleslaw, 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 coleslaw. Okay, so where is the cosine 0? It looks like it's 0 at pi over 2 and at, negative pi over 2. So those are the two no-nos. So our interval for the domain, it can't be, it's not allowed to be 0. So the domain x cannot equal pi over 2, and x cannot equal negative pi over 2. Or 3 pi over 2, if you want to go around the positive way. All right. Okay, so then let's do it to it. Take the derivative. First derivative is 2 minus 2 times the derivative of tangent is secant squared x. And then it's times that, but that's just 1. So that's it. That is the first derivative. We could rewrite it. Like this. So it's a little easier to take the derivative when it looks like that. That means that. All right, so second derivative, that's gone. This times this, negative 4. And then we write the secant x. And then we take 1 off of there, so 1. But then we have to multiply it by the derivative of what's inside there. And the derivative of secant is secant tangent. Okie dokie. And now clean it up. So y double prime is -4 secant times secant squared x tangent x. And so that's what we're looking at. And so we set that equal to 0. That is not going to be that easy. All right, so what are we looking at here? We've got set them equal to 0, cosine. Let's change them to sines and cosines. This is too confusing with this stuff. We'd have to look at the secondary thing. So here, this is 1 over cosine squared. And this is sine over cosine. All right, and then that'll be easier. This will be easier to find zeros because now we have the sine of x. You can just set that equal to 0, and cosine cubed x. You can just set that equal to 0. And so that's a little easier. So let's set those both equal to 0. So we got -4 sine x equals 0. So you divide out the -4, that just disappears. So sine x equals 0. When is the sine equal to 0? Well, that is at 0 and pi, right? This is pi over 2. This is pi. This is -pi over 2. Except the interval only goes from here to there. So pi gets kicked out. And so we'd have x is equal to 0 and x is equal to pi. But pi is outside of our interval. This is -90 to 90. That's 180. Not in the interval. So here's one critical number that we're going to look at as a possible inflection point. And what about cosine cubed? So cosine cubed of x equal to 0, set that equal to 0. And we take the cube root of both sides, and that's just 0. And so you got the cosine of x equal to 0. So where is the cosine 0? Well, that's 0 at -90 and 90, except those are our endpoints, and it's not inclusive. So those are not in the domain. Because those aren't brackets, those are parentheses. So not in our interval. I said domain, not in our interval. Not in the interval. So we got to kick that out, kick that out. Well, that simplified our problem a bit then. So now we're only looking at x equals 0 on our number line. Put a big old dark arrow at x equals 0. And then something to the right, something to the left, 1, -1. This is -infinity to 0. This is 0 to infinity. Make sure you just base that off of the possible inflection point. Students pick these numbers, 1, 2, 3, and then they'll put that in there, and they'll say, oh, and from -1 to 1, those aren't critical numbers. Those are numbers you just picked that were in the interval, just to test the second derivative with. So now we take the second derivative, this guy, and we pop in, oh, let's not use 1. We can use anything we want. Let's use something we know. We can't use 0 either. 0 would have been good. But let's use like pi over 4. How about 45 degrees? That'll be easier. Oh, positive though. So pi over 4. Not 1. Pi over 4. Pi over 4. And negative pi over 4. So now let's put those in. We got y double prime is equal to -4 times the sine of -45 degrees, negative pi over 4, over the cosine of negative pi over 4 cubed. like that. So remember pi over 4, that's the square root of 2 over 2, right? So when I'm doing that, the square root of 2 over 2, all-star trig class, 45 degrees, negative 45 degrees. That's actually in this quadrant. All-star trig class. And so the sine negative 45, that's going to be negative square root of 2 over 2 times negative 4 divided by, and cosine, that's going to be positive square root of 2 over 2. And that's going to be cubed. And we got to see, is that positive or is that negative? And at the end of the day, a negative times a negative is a positive. And yeah, so overall, that's going to be a positive number. Because, right, positive number, it's ugly, but cubed and divided by that. And so we're just going to go with positive. Greater than 0. So if that is greater than 0, that is a plus. That is concave up. All right. Y double prime, we're going to put in just negative 4 times the sine of 45 degrees over the cosine of 45 degrees. And then cube it. So again, that is the square root of 2 over 2 times negative 4. That's negative 2 square root of 2 divided by the square root of 2 over 2 cubed. So a negative divided by a positive, that's a negative. That's going to be less than 0. That means this is a negative value, and so it is concave down, which means 0 is our point of inflection. So it's concave up on the interval from here. Let's write our answer here. We'll put our conclusion over here in the corner. So what do we have? We have concave up from negative infinity to 0. We have concave down from 0 to infinity. And we have an inflection point at x equals 0. Okie dokie. Oh, but it's not infinity. Oh, shoot skis. I forgot about the interval they put us on. So little insert here. We don't get to go all the way to infinity on these. They restricted us. So negative pi over 2, pi over 2 is the interval. Sorry about that. So from negative 90 to 0, from 0 to 90, that's the concavity. But then at x equals 0, there's a inflection point. Okie dokie. I gotta add parentheses on my little note packet. All right, number 6. Whew. So the natural log E. How are we doing for time? Okay, 49. After you get the hang of these, they can be tedious, but that's a lot of calculus is kind of tedious. I hope it's not too difficult to get your head around what we're doing. It's just there's a lot of steps. It's tedious work, and you really have to be precise. You know, everybody kind of throws that out about math being nitpicky, and it is. It is a precise science, and so nitpicky is a good description. Okay, so what do we want to do here? let's rewrite it. And then we'll do the derivative. So instead of saying over 2, let's call it f of x is equal to 1/2 e to the x minus e to the negative x. And now let's do the derivative. Remember the derivative of e to the x. It's its own derivative. So we did the derivative of that. It's that. For this, we take the negative and multiply it times that. So the negative 1 times that. So we get plus e to the negative x. But then you have to multiply by the derivative of negative x, which is negative 1. So we took the negative 1, multiplied it in the front, and then it's its own derivative. So that's why it just stays e to the negative x. But then you have to multiply by the derivative of the power. I did it here too. It's just the derivative of x is 1. And so 1 times e to the x is just e to the x. So we almost never put it there. But because they slipped that little negative in there, that changed the sign in the front. And I had to multiply by negative 1, so it's going to change right back. And so the first derivative is that. All right, and so now we're going to do the second derivative. And you may have noticed that this is the same as that at the end of the day. So guess what? It's itself again. All right. So now let me see what we're gonna do to think about critical numbers. Yeah, there's a couple of ways to go at this. You can factor out an e to the negative x. I think that's actually more confusing than this. Let me show you this way. I think this way is a little easier. We'll see what you think. E to the x over 1 minus 1 over e to the x. That's what that is, right? And now let's do a common denominator, which is e to the x. So multiply top and bottom of this by e to the x. And then you get this, e to the, right, there's 2 of them, so 2x. Minus 1 over e to the x, because we have the common denominator now. And that's still all over 2. And you're like, well, I don't want to have a 2 on the bottom, so let's multiply by the reciprocal, top and bottom, and then, right, that goes away. So we end up with this. E to the 2x minus 1 over 2e to the x. Okie dokie. Now we're going to set both of that, both the numerator and the denominator, to 0 and see what it shakes out. 2x minus 1 equals 0. So set equal to 0. We're just doing it up here. So I move the 1 over. So I got e to the negative, e to the 2x is equal to 1. Well, anything to the 0 power is equal to 1, right? Or you could do ln. So you could just logic this and just say x equals 0, because e to the 0 power is 1. But if you want, you could do like the natural log of both sides, something like that. I don't know if that makes it easier. And then pull that 2x down in front. ln e is 1. The natural log of 1 is 0. Divide by the 2. And it's kind of the long way around. If you just went from here and just said x equals 0 without this work, that would be okay. Because I know, you know what you're doing, hopefully. And then the other one, 2e to the x is equal to 0. And so divide by 2, and that's sort of the same thing, right? So what would x have to be to get a 0 there? That would have to be 2 e to the x, e to the 0. Oh, wait. No. I'm thinking 1. The 1 is 0. This is, you can't. This is no solution. You can't do that. You can't take 2.7 blah, blah, blah to some power and get 0. You could get it really close to 0. You could take it to the negative 1 billionth power. And then that would be really, really close to 0, but it wouldn't be 0. And so you can't take a number to some power and get it to 0. And so there's no solution for that part. So we're only looking at this. That is our possible inflection point. 0, let's go negative 1, positive 1. And now I'm going to throw those into f double prime. So f double prime of negative 1, that is negative infinity to 0, that interval, and 0 to positive infinity. And so when I put in a negative 1, I get, what do I get? E to the negative 2 minus 1 over 2e to the negative 1. And if you click that into your calculator, you're going to get like negative 0.865 on the top and 0.785 on the bottom. That's going to be approximately negative 1.18, which is less than 0. So f double prime of negative 1 is less than 0, which means this is negative, which means we're talking about concave down. And then f double prime of positive 1 is e to the second minus 1 over 2e to the first. And that turns out to be positive 1.18, approximately. Which means that f double prime of positive 1 is greater than 0. Which means that's positive, which means that is concave up. Which means we do have an inflection point there. I never leave enough room for my conclusion. So we conclude that we're talking concave down on the interval negative infinity to 0, concave up, 0 to infinity, and inflection point at x equals 0. Okie dokie. So pretty tedious problems. Let's take a look at page 20, the second derivative test. Okay, so instead of doing the little is it increasing or is it decreasing off of the first derivative to determine whether it's a local max or a local min, we could play with the second derivative and look at the concavity. Because look, if it's concave up and you have a critical point in that interval, that's going to be a max. If it's concave down, that's going to be a max. Concave up, that's going to be a min. And so it kind of depends on the problem. Neither one is more correct. You can use the concavity test to determine whether it's a local max or local min by taking the second derivative. But if it's easier to just look at the intervals off of the first derivative to see if they're increasing or decreasing, you can just do it that way too to determine whether it's a relative max or relative min. So let's see. They have relative. This book always uses local. So on the top of page 20, if you want to cross off the word relative and put local over it, that's fine. Local min, local max. F may have a local maximum, a local minimum, or neither at x naught. So x naught is a critical number. So we're looking at critical numbers. So we're doing the same thing that we were just doing. just applying it to the second derivative. And so this is interesting. Let's see what let's write up some stuff here. The first derivative, intervals of increasing, decreasing critical numbers and local extrema. So local min or local max. Those are things that you can find from the first derivative. The second derivative, intervals of concavity, intervals of concave up or concave down, and we can find IPs, inflection points, and local extrema. Ooh, so see, we could just use the second derivative to find if it's a local max or local min, or we could do the first derivative and just check on either side of our critical number to see if it's increasing or decreasing. If we get a decreasing and then an increasing, then we know it's a minimum local min. If it's increasing and then decreasing, we know it's a local max, but we could do the same thing with concavity. All right, and so look, they have the original and the next one and the next one. Let's see, the original is y equals 2x cubed plus 3x squared minus 12x. And they have the graph for us that looks like this. Okay, that's great. We got an inflection point there, and a max and a min. Then they graphed the second derivative, or the first derivative, y prime is 6x squared plus 6x minus 12. And that looked like this. So that was a parabola opening up. And then they took the second derivative, and that was 12x plus 6. And that's just a line, a steep line, like that. So now look, these are all related. They're all related. Where is this decreasing? The original graph is decreasing from -2 to -1. Or to +1, sorry, positive one. So decreasing from -2 to +1. That is a decreasing interval. If we take a look at where f prime is below the x-axis, it's below the x-axis from -2 to +1. And so the first derivative is negative, means you're on a decreasing interval on the original. So when this is below the x-axis, this is the decreasing interval. All right. The second derivative. Oh wait, so that's all we're gonna get off of that until we get down to local maxes, and then we can look at concavity on the bottom. All right, so let's do increasing now. So it's increasing from -infinity to -2 in union with 1 to infinity. But again, if we take a look at f prime is greater than 0 from, it's above the x-axis from -infinity up to -2. It's above the x-axis from 1 to infinity. So this same interval, this is true. F prime is greater than 0. All right. Okay. So now let's look at the local max and the local min. So we have a local max at x equals -2 and a local min at x equals 1. Well, f prime is equal to 0 at x equals -2. F prime is equal to 0 at x equals 1. So in the graph, when those are zeros, those flag. Remember, that is the slope of the tangent line on the curve at that point. Instantaneous rate of change there. And so those are both 0. First derivative equal to 0 gives you maxes and mins, local max and local min. All right. What else do we know? X is, oh, you can tell whether it's a max or a min if you're going positive to negative, or, so look, for -2, if I said, okay, well, f prime is going from positive to negative. So it's not as obvious here. It's a little more obvious when you're looking on the number line thing and saying, okay, here's -2. And if it's going from positive to negative, you know, that's, here we know it's going from positive to negative is the transition. But when you look at it as a positive to a negative like this, it's a little more obvious that it's a max because it kind of peaks there, you know. And same if it goes from negative to positive, then we know it's a local minimum here. So from positive to negative, it's a local max. From negative to positive, so when we were here and it was going down from negative to positive, then, you know, you could kind of see it's a low point, a local min. So it does matter, like the transitioning as you go from left to right. If it's going from negative to positive, you can determine it. It's just easier to see on our number line thing than it is on the actual graph, I think. All right. And now let's talk about concavity. So if f double prime, f is concave down, f double prime, so let's look at that. I'll use red. I didn't use red yet. Okay, so here. F is concave down. What does that mean? Concave down is here, like this. It's that little bumpy guy right there. That's concave down. And if you look at that interval, that is from negative infinity to, it looks like -1/2. All right. And that's also where f double prime is less than 0. That is -1/2 right there. And it's below the x-axis. So where the second derivative is less than 0 or negative, then the graph itself is concave down. F is concave up from -1/2 to positive infinity. That means this would all hold water, right? That part. It's like that. And that is on the second derivative is above the x-axis from there. So that is positive, above 0. Okie dokie. That's page 20. Yeah, those are kind of cool. I've seen some kind of cool simulations where they put those in there and you can move this graph around and it changes those too as you pull it forward or backward or what have you. Okay, let's do page 21 and finish this lecture off. So we are going to take the second derivative and put in our critical number. And let's look at those problems. Oh, 2 problems left. Let's finish her off. We got number 8. F of x is equal to negative x cubed plus x squared minus 15x. And they want us to do a bunch of stuff. All right. So let's take the first derivative. 3x squared plus 14x minus 15. And let's set that equal to 0. And that will determine our critical numbers. So, factoring with 15. This one's a bear. Factor out a -1. And you get 3x squared minus 14x plus 15. And we want that equal to 0. And so now it's going to work out to be 3x and x. And then we want 15. So let's put the 5 here and the 3 there. And that should get us where we want, right? 9 and 5 is 14. And both negatives. A negative times negative is a positive. All right, and so we end up with 2 critical values. So x is equal to 3, x is equal to 5/3, or 1 2/3. And so let's put those on our number line. So 1 2/3, 5/3, and 3. Number in between there is, how about 2? And again, this interval here, it breaks it into 3 intervals. 5/3 to 3, 3 to infinity, and negative infinity to 5/3. So 3 intervals we got broken up. Anything less than 5/3, how about 0? Anything bigger than 3, how about 4? And so let's find all of these. So f prime of 0. So I put 0 in. Again, when you're subbing it in, instead of, especially when we're just worried about positives or negatives, I want to get this number. So instead of, I mean, this one, 0 is easy because I can just crank it in and get negative 15. And then I know it's less than 0. So f prime of 0 is less than 0, which means that's negative, which means I know it's decreasing. All right, so 0 is different, but for the next one, for 2, when I'm going to put in 2, because, mark these with arrows. Sorry. You should mark those with arrows. Your critical numbers, put like some distinction, like arrows, so you don't mix them up. All right, and these were just numbers you just picked. You could have picked 5 or 7 or 10 or 2.5. Don't know why you'd pick that. Or negative 20. Anything in the interval would work out to be the same when you sub it in. All right, so now let's do f prime of 2. So here's what I was getting at before. Instead of going back to this and putting in a 2 and squaring it and everything, go to this. Go to the factored form. Because now look, this is -1. You can write them down, right? 2 minus 3 is -1. 6 minus 5 is +1. and the negative 1 is there. And so that's just 1, which is way easier than subbing it into the original. And so that is greater than 0. So we got f prime of 2 is greater than 0. So that is positive, which means this is an increasing interval. So decreasing and increasing, which means that's going to be a local min. And then let's look at 4. Pop in a 4, f prime of 4. And again, go back up here and just put in the 4 there and there. And so you got -1 times 12 minus 5 is 7. And then 4 minus 3 is 1. It's -7. And so that's super easy. That's easier than going back up. I think we're too used to subbing it back into the original thing and squaring it and multiplying it by -3 and multiplying it by 14 and taking off 15, when it's a lot easier to throw these in and just do these numbers in your head. You don't even need your calculator. And so f prime of 4 is less than 0. It's less than 0. And so that's negative. So that means it's decreasing. So that means 3 is a local max. So we got a local min at x equals 1 2/3 or 5/3. We got a local max at x equals 3. And now they want us to find the inflection point and confirm that this is really a min and this is really a max. And we can do that. So let's take the second derivative. So now we do want to go back to here to do the derivative. So -6x plus 14, set that equal to 0. So -6x equals -14 divided by -6. So x is equal to 7/3. 2 1/3. And so we're looking at, again, mark down our critical number. Something bigger than that, 3, that's 2 1/3. Something smaller, 0. And now you're subbing those values in. Remember, this interval is -infinity to 7/3. This one is 7/3 to positive infinity. And now when I put in the 0, I'm going back up there. And that is 14. So f double prime of 0 is 14, which is greater than 0. So f double prime of 0 is positive. A positive value means concave up, which confirms that this is a min. 1 2/3 is a min, because 1 2/3 falls into this category. That goes to 2 1/3. So if it's on this interval that is concave up, it's got to be a minimum. This one, f double prime of 3. -18 plus 14 is -4. So that is less than 0. That is negative, so that is concave down. That again confirms where this 3 is bigger than 2 1/3, so that's in this interval. And if that is a critical number in this interval, that has to be a max. It's got to be up on the tippy top, right, of the concavity. This one has to be on the bottom of the concavity. So you can use the concavity test and skip this if we're going to make you find inflection points. You don't have to do this and this. You could just do the first derivative, set it equal to 0, find the critical numbers, and mark them down, but then put a hold on it and then do the concavity and see where those fall. And determine whether they're maxes or mins off of that. All right. Okay, so what are we looking at? Concave up from negative infinity to 7/3. Concave down from 7/3 to positive infinity. And inflection point at x equals 7/3. Okay, let's do the last one. 8/9. So, last one on page 21. Number 9. So the first derivative is 8/9 x to the negative 1/9. We can rewrite that. 8/9 x to the 1/9. Set that equal to 0. Find the asymptote. So we have 9x to the 1/9 is equal to 0. And so you can divide out the 9 and take the 9th, take it to the 9th power. And x equals 0. That is a critical number. So we've got 0. So this is negative infinity to 0. This is 0 to infinity. And how about negative 1 and positive 1? F prime of 1. And we put in 1. The 9th root of 1 is 1. So that's just 8/9, which is greater than 0. So that's positive. Wait, I got a negative on there. Oh, I put in that. This is positive. F prime of, let's just make it negative 1 and negative less than 0. That's going to be too confusing. Okay, so this one's positive, this one's negative. And so decreasing, increasing. So a local min at x equals 0. All right. So now let's look at f double prime of x. So we're going off of this, multiply that times that, and we get negative 8/9 times, 8/9 times negative 1/9 x to the negative 1/9 minus 9/9 is negative 10/9. So that is negative 8/81 x to the 10/9 on the bottom. That is a doozy. So now, second derivative test, we want to try, what are we trying to do here? So if we take our critical number, our second derivative test, we get the second derivative. If we take our critical number and sub it in there, what's going to happen? It does not exist. So we got a DNE. The second derivative test only works for critical numbers where f prime of x equals 0, not where critical numbers were f prime of x does not exist. Then use the first derivative test instead. So basically, you cannot use the concavity test when you've got something that's like an asymptote that's going to crash it. So we had to do this method. We couldn't use the concavity method with that one. All right. Whew, that was 4.5. That was one long section.